All right. Hello, everyone. Welcome to VSPG. Today, we have a presentation from Michiel De Kock. He's presenting on extreme high latitude platform carbonate deposition, climate paradox at the terminal Mesoproterozoic. So I'm going to go ahead and introduce Michiel for us. Michiel is a paleomagnetist, sedimentologist, and stratigrapher interested in the interplay between global tectonics, the biosphere, and surface processes through time. He focuses on the application of paleomagnetism to unravel the effect of tectonics on Earth's surface environments. Recently, for Michiel, large igneous provinces have been a central research target, along with their impact on atmospheric and biospheric evolution. Today, Michiel will discuss paleomagnetic data on a 1.2 billion-year-old carbonate platform and what this may indicate for paleoclimate at this time in Earth history. Michiel received his master's in geology from Rand Afrikaans University in South Africa and his PhD in petrology from the University of Johannesburg in South Africa. His thesis for his PhD was titled Paleomagnetism of Selected Neo-Archean Paleoproterozoic Cover Sequences on the Cap-Val Craton and Implications for Valbara. After his PhD, Michiel was a postdoctoral scholar at Yale University prior to becoming a lecturer and soon thereafter associate professor at the University of Johannesburg. Today, he continues his research at the University of Johannesburg while also teaching sedimentology, basin analysis, plate tectonics, and geological field techniques. So we're really excited to have you today, Michiel. So please go ahead and get started with presenting.
Yeah, thank you very much, Alex, and thank you everybody for the opportunity to present on this platform. So let's see. So first of all, this talk and this work wouldn't have been possible without several people, particularly Professor Nick Beekes, whose ideas and discussions with him really shaped my ideas about these rocks from India. Unfortunately, several of my co-workers who worked with me on these rocks passed away in the last 2 years, and this talk is really dedicated to them. So first of all, this is just an outline of my talk, and I'm going to start off with a brief introduction on shallow marine carbonate platforms, and then look at the geology of the Mesoproterozoic geology of India, from where I will be presenting some paleomagnetic results, and then looking at what those actually mean. So today, carbonate accumulation in the present day oceans extends basically as a continuum from low latitude to high latitude, and from shallow shelves, shallow platforms, all the way to pelagic environments. But pelagic carbonates are not particularly well preserved in the geological record, particularly before the Jurassic. So most of the carbonates that we have in the geological record are actually shallow shelf carbonates. And these shallow shelf carbonates, we can differentiate between high latitude cold water carbonates, and these are low latitude warm water carbonates. So the high latitude carbonates are in principle heterozoan, and they typically bioclastic, okay, and they are associated with today with ahematypic corals, so corals that don't build big coral reefs, and they typically devoid of lime muds and ooids. Okay, the shallow, the low latitude warm carbonates, on the other hand, are more photozoan association with autotrophic carbonate producers like green calcareous algae, but also invertebrates and photosymbiont hematypic corals, so corals that build big reefs, together with lime muds, primary precipitates of lime mud, and ooids. Okay, so the divide that we see typically between cold and warm water carbonates today, it's a little bit diffuse, but typically most people place it at around water temperature depths of water temperatures of about 20 degrees Celsius. So these warm water carbonates that occur within 30 degrees of the equator are actually the principal setting for carbonate production in the Phanerozoic and for carbonate preservation. So carbonate deposition is clearly favored in warm, shallow seas and occurred during the Phanerozoic preferentially from tropical to subtropical shelves throughout this period. And this has been shown by studies by Kiesling, who did a review of these things, as well as Ziegler in 2003. Now, most people assume that Precambrian carbonate platforms acted in the same way, that they are analogous to modern warm water platforms. And they share a lot of similarities. So, for example, they share similar facies belts, particulate and muddy sediments, oohoids, reefs. The Precambrian ones, the reefs were built by stromatolites, but also seafloor cement precipitation like aragonite fans and molotov structures, but also through stratigraphic stacking patterns. And most paleogeographers assume that Precambrian carbonates also formed in tropical and subtropical shelves throughout the Precambrian. So this is just one example looking at the Congo craton and the San Francisco craton through time, its drift through time. And what you can see is that together with the occurrences of carbonate basins, big carbonate basins, wherever we have paleomagnetic data, that continental block is sitting within the tropics and subtropics. And so we assume this to be true for most of the Precambrian, but today I'm going to be showing you some results from India that is supporting the development of voluminous carbonate platforms, shallow marine carbonate platforms at a much higher latitude of something like 70 degrees north of the equator. So to get into that, I'd like to introduce a little bit the geology, the Mesoproterozoic geology of India. And so if we look at India, India is basically composed out of two big cratonic blocks, southern India and northern India, and both of these have been stitched together by the central Indian tectonic zone, okay, which is this polymetamorphic belt that formed between 2 billion years all the way to about 900 million years. And it's only at about 1,000 to 900 million years that these two blocks were welded together, the North Indian craton or North Indian shield and the Southern Indian shield. And so if we look at the geology of India, particularly Southern India, which is made up of the Dharwad craton, Bastar craton, and Singhbum craton, we find several Proterozoic cover successions on top preserved on southern India. And these Proterozoic successions have generally been named the Purana basins, and they are really largely unmetamorphosed, undeformed basins of clastics as well as chemical sediments. And in the northern India, we also find these Purana basins or Proterozoic basins. Here it is the Vindhyan and Marwar basins, but what we have to realize is that the northern Purana basins of northern India doesn't really have anything to do with the Purana basins of southern India, because these two blocks were not together during much of the Mesoproterozoic. So in southern India, these Purana basins is made up of several unconformity-bounded sequences, and one of these sequences, sequence 3, is very well developed in multiple basins across southern India. And this sequence 3, if we look closer to what it is composed of, it's basically at its base, it has a marine sandstone, followed by a succession of carbonates and shales, and it can be correlated across most of southern India, all the way from the Bhima and Kalathi basin to the Kadapa, through the Pranita Godavari basin, the Chhattisgarh basin, all the way possibly to the Singhbum craton, to the Kolan basin. Okay, and so these carbonates that are preserved in these basins, all these basins are typically lime mudstones, very well-bedded lime mudstones that were deposited in fairly deep water below wave base, typically. And what we typically see in these carbonates is we see a stratigraphic color variation. They typically start off as being brown to pinkish in color, and then they transition over to black limestones, going through a steel gray facies, and then often they go back into brown or pink limestones at the top and become increasingly calcareous shales as you go towards the top. In some of these basins, there's another sequence of or cycle of carbonate deposition preserved in some of them, but not in all of them. Okay, so typically, if one look at the depositional environment of these carbonates, they sort of in a deposited on a ramp, okay, below fair weather wave base. And what you see is one sees spatially limited development of some branching stromatolites, but it's only in a very few localities where that is preserved. Most often you get this very monotone, horizontally extensive tabular bedded limestones that in some places have these calc limestone classed conglomerates, okay, which are interpreted as mass flow deposits that occurred sort of in the overly steepened settings of a ramp, okay, and the darker black limestones and gray limestones are interpreted to be associated with sort of an oxygen minimum zone on the outer ramp, okay. So this platform, which we call the Purana platform, is actually well dated fairly well dated in the Chhattisgarh and Indravati basins, particularly its top. There's some felsic tuffs that have given ages of about 1 billion to about 990, so around 1 billion is closure of these basins. And in the Chhattisgarh basin, there's another tuff that has been dated at its base that sort of constrain the start of these basins sometime after 1,400 million years. In the Penganga, in the Pranita Godavari basin, at its base, there's some glauconitic sandstones, and these glauconitic sandstones actually give a minimum constrained argon-argon age of about 1180, which is a minimum constraint for the platform in the Pranita Godavari basin. The trital zircon ages from the Kolan are also around 1160, and so probably the Kolan basin was deposited at the same time. The ages of the Kalatji, the Bhima, and the Kadapa basin is not as well constrained, but is generally assigned between the latest Mesoproterozoic and early New Proterozoic. But paleomagnetic data from these basins suggest that they are correlatives of the Pranita Godavari Valley Basin, as well as the Indravati and the Chhattisgarh Basin of a Bastard Craton. So the data that I'm going to be presenting today is coming from the Kadapa Basin, and so I'm going to zoom in now on the Kadapa Basin. And here you can see where our samples are from, but the Kadapa Basin is geology. It's basically made up of three main units. So the oldest unit in the Kadapa Basin is the which occurs here sort of on this belly shaped or this big C-shaped outcrop pattern here. And this is the Papakni and Chatrivati groups of the Kadapa Basin, and they are intruded by a series of mafic sills that have been dated very accurately with bedelite at 1885. So this is a real Paleoproterozoic succession, and it's followed by shallow marine clastics of a Gandikota formation, which also look very similar to the shallow marine clastics of a Srishalanam formation, and both of these aren't very well dated. But they also probably around sort of late Paleoproterozoic in age. Then the youngest units in the Kadapa Basin is here indicated by blue. Okay, but before I get to them, they have been juxtaposed. All of these units of a Karapa basin have been juxtaposed against these deformed Nalamalai group, okay, which is a autochthonous unit that have been emplaced by thrusts at about 1 billion years ago. Okay, and so, but these rocks of a Nalamalai group are around 15 to 1600 million years old. And this is based on detrital zircons, but also on ages for some of these granites that intrude the Nalamalai, like the Velaturu granite, which occurs here sort of in the north of the Nalamalai fold belt. So these two youngest units is actually our sequence 3, which is making part of this and was part of this Purana platform, carbonate platform that developed across the whole of southern India. And so this is the Karnool group in the Karapa Basin, and the Karnool group is preserved in 2 areas. It's preserved in the Karnool Basin and the Palnat Basin. And of course, it starts at its bottom with a shallow marine sandstone that goes into carbonates. And so here you can see some of the carbonates, which is called the Narji Formation in these 2 basins. So the Narji formations typically start off with these pink limestones, often interbedded with some siliciclastics, and then it goes over quite quickly into its most common appearance throughout this throughout the outcrop area, which is these black and gray limestones, which is being mined here for building stone, called the Karapa stone, but it's essentially these black limestones. So here you can see it in stratigraphic column. So you start off with a Banganapali formation, which is this sandstone going into pink carbonates, sometimes with these calc limestone conglomerates going into gray and black limestone. And in the Karnool group, so in this area, the unit is more complete. So here you actually go over into a shale called the Oak Shale, and that's followed by another cycle of sandstone and limestone going into calcareous shale at the top. In the Palnat Basin, we really only see the gray limestones in the Narji Formation, so we don't see all the color variation over here. So the ages, like I said, is not very well constrained. So there is some detrital zircon data available from the Banganapali sandstone at the bottom, which places it sometime after 1700, sometime after 1300, 1,300 million years ago. And then there's also some detrital zircons available from this sandstone, the second sandstone cycle in the Karnool Basin, called the Paniam. And here a single detrital zircon was reported at about 900 million years, but probably a more conservative estimate is actually a bigger population of concordant zircons, which is the next youngest one. It's about 1700 million years ago. That's probably a better constraint because this is only based on one single zircon from the Paniam. And then from the Oak Shale, there's also some microfossils. These Ubrushevela microfossils, which are these coiled microfossils, and they actually suggest a Neoproterozoic, late Neoproterozoic age for the Oak Shale. So the Narji formation is probably older than about the late Neoproterozoic. And the paleomagnetic data, which I'll be showing, will actually support an older age, a Mesoproterozoic age of about 1.2 for the Narji formation. So geochemically, we don't have a lot of geochemical data, and this is something that we really need to actually get some more data from. But the limestones, the chemistry of the limestones, whether they are pink or gray or black, they typically give these rare earth element patterns that reflect seawater composition. So in other words, they have negative cerium anomalies, positive yttrium anomalies. So they were deposited from seawater. and they still reflect that. In terms of stable isotopes, stable carbon isotopes, they typically, again, there's not a lot of data, but they sit typically around slightly on the positive side, so around carbon of delta 13C values of around 2 or just below 2. So they sit slightly on the positive side. And again, if we just compare to the evolution of delta 13C through time, this typically, you would expect this type of signature at the end of a Mesoproterozoic towards the early Neoproterozoic. So let's look at some of the paleomagnetic data. And so we sampled both areas, the Nachi Formation and Banganapali Formation in the Karnool Basin. And we have a fair number of sites. So this is just showing you where we actually sampled, mostly concentrated in the Nachi and the Banganapali, so the lower part of a succession in the Karnool. And in Palnat, we also have several sampling sites within the Banganapali and the Nachi Formation. And so when we started demagnetizing these limestones and also the sandstones of the Banganapali, we see that they are typically record two magnetic components. So there's a low temperature component indicated in all these diagrams as these blue arrows, okay, and a high temperature component, which in the pink limestones typically remains stable up to about 600 degrees or sometimes above 600 degrees Celsius, and in the sandstones as well as in the gray and black limestones it remains stable only till about 400. Okay, and so that is just to do with the magnetic mineralogy of these two lithologies. But what you can see is that the low stability component is always sort of northerly directed and fairly shallow, right? So fairly shallow northerly directed component, where the high temperature component is downwards, okay, and fairly steep. So fairly steep northerly direction in both of these sites. So fairly steep northerly and downwards in both of these sites. We also see in some sample sites that the high temperature component is actually, in some of them, it's southerly and steeply upwards pointing. So we're probably getting two polarities of this direction being recorded. So in particularly towards the bottom, we tend to see these southerly steep up directions, and towards the top we see these steep downward, more northerly directions. And again, we see them in both the pink limestones as well as in the black and gray limestones. The only difference between the two is the magnetic carrier. So the magnetic carrier here in the pink limestones is probably hematite, based on its stability above 600 degrees Celsius demagnetization. And in the black limestones, it is probably a magnetite that is carrying the remnants. Okay, and so here you can see just a summary of all the different sites, and typically the blue ones is the low stability component, so always sort of northerly and fairly shallow. And then the high temperature components are always very steep, either southerly and upwards or northerly and downwards, as in most of the sites. And the northerly down component seems to be the more common or more commonly developed direction that we see in these. And just to confirm our magnetic mineralogy, we also did some thermomagnetic curves. So here for the pink calcareous shale, during heating, you lose magnetic susceptibility, or the magnetic susceptibility drops significantly after about 660 degrees, confirming that we're probably dealing with hematite as a carrier of the remnants. And in the black limestones, you see this drop occurring at about during heating. So here's just the heating part of the curve shown, and at about 580, which suggests that this is probably magnetite that is the carrier of the high temperature remnants that is recorded by these limestones. So some of the gray limestones have a little bit more complicated magnetic mineralogy. Again, they have basically 545, 580, these drops. not as well discernible, but again, that is probably related to magnetite, where some of them show an earlier drop at about 400 degrees, and that might be actually related to some sulfite, something like pyrrhotite, that might be also contributing towards the remnants in these rocks. So whenever we get these magnetic directions, these high temperature directions, of course, we need to do field tests to figure out if they are primary or what is the timing of their magnetization. And so for the rocks of Nargi, we were able to do actually a fold test in the field. So you can see this fold with about 14 samples taken along this same bed, okay? And the idea is with a fold test, for those of you who are not familiar with it, is, of course, if your magnetization was recorded before the folding, okay, it would actually be folded by this deformation. And so it should actually be fairly distributed in rocks just viewed in situ. So here you can see that high temperature, that southerly down high temperature component, and yeah, or sort of normally down high temperature component. So just a very steep component, but you can see how these individual samples that record this direction are quite distributed, okay? And when we tilt correct these beds and the magnetization carried in these samples, we can see that they actually cluster a lot better. And so when we actually evaluate this precision of the clustering of the data, we can actually see that there's a significant increase in the clustering of the data upon correction of the tilting, which suggests that this direction was recorded before the folding occurred here in the Nargi. And so remember, the last big tectonic event that actually affected these mostly undeformed limestones is actually this thrusting of a nullamalai group onto the other units of a Katapa basin. And that thrusting probably happened at about 1 billion years. So this is probably, we're looking at a magnetic direction that's older than 1 billion that is recorded by these limestones here. We were also able to do some conglomerate tests on these lime class conglomerates. So here you can see some of these individual clasts that we sampled. And again, if a magnetization was primary, it would actually, when you form the conglomerate, you would actually randomize the magnetic direction in the individual clasts. So here we can see the underlying limestone showing the low temperature direction, which is sort of normally fairly shallow, and the high temperature direction, which in this case is very steep southerly. And if we look at the individual clasts, we can see they all record, of course, the low temperature direction, which is probably a present geomagnetic field overprint on these samples. But at high temperature, the clasts are showing no grouping really at all. They are fairly random. So this is a positive conglomerate test, and it's an intraformational conglomerate. So it really supports the idea that this high temperature direction is really primary. Okay, and so you might have noticed that this primary direction from the Nargi group is exceedingly steep. Okay, so it is really a steep direction, and so in paleomag, these steep directions typically form quite high paleolatitudes. Okay, and so that started us thinking a little bit. But not only do we have these directions from the Carnot group, so these very steep directions and dual polarity directions supported by field tests, we have similar directions from the Kalatji and Bima basin. Here we don't have field tests, but again, we have both polarities preserved there. And then also in the Chhattisgarh and Pranita Godavari Valley basin, so that is basin 5 and basin 7 here on the map, we see these same directions being recorded, and again we see both polarities. In the Chhattisgarh basin, we also have a very nice positive conglomerate test. So again, the underlying pink limestones here, you can see they show that present field overprint. They show another low temperature overprint that we didn't see in Carnot. But at high temperature, they give us very steep southerly up or very steep northerly down directions, okay? And if we sample these clasts in this limestone mass flow deposit, so you can see all these clasts in here, and the individual samples from individual clasts are again showing the present field overprint as well as this second low temperature overprint. But at high temperature, the clasts show no grouping at all, suggesting that they've been randomized during the formation of a conglomerate. And here the conglomerate is actually overlain by a little draping bed of pink limestone on top, and we also sampled that. And that limestone again shows the present field overprint, the second low temperature overprint, and at high temperature it shows the northerly steep directions. So this, we're fairly sure that these directions, these high temperature directions, are primary because they give this very nice positive intraformational conglomerate test. What's more is these individual conglomerate clasts, one can actually see bedding in them. And so if we correct the clast back to paleohorizontal, of course, we don't know how it has rotated around the vertical axis. But if we correct them for bedding, we can actually see that they all cluster at very tight, a very steep inclination. So when the individual clasts are restored to paleohorizontal, you can see this is the inclination recorded in the clasts, which looks exactly the same as the inclination that is recorded in the underlying conglomerate, and it is just slightly different from the inclination in the overlying conglomerate, but all of them are very, very steep. So it's a really, really strong positive intraformational conglomerate test. So if we look at those directions that we got, so yeah, we think they're primary, but to make sure they're not representing paleomagnetic or magnetic overprints, we have to compare them with younger poles that are available from India, from southern India in particular. And so if we look at our two directions that we got from the Carnoul, and we convert them to virtual geomagnetic poles, we can actually see our low temperature component, which we think is a present field overprint. Of course, it actually sits very close to the spin axis and sits very close to the modern day North Pole, where the high temperature component looks very different from all the Phanerozoic poles for Gondwana land, here placed into an Indian reference frame. So you can see this high temperature component doesn't resemble anything Phanerozoic. It also doesn't, if we compare it to Precambrian poles from India, there's of course not such a big database, but we can compare it to key paleomagnetic poles, so very well-defined, well-dated paleomagnetic poles from India, and it doesn't look like any of these poles. So it doesn't look like the 1465 million year old pole. It doesn't look like the 1,075,000,000, and it doesn't look like 770. It does share some similarity with a pole from a group of alkaline dikes called the Harihaldi alkaline dikes from southern India. And these dikes, one of these dikes have been dated actually with badleite at 1192. The problem is, of course, this is a dike swarm, and the dike that was dated, which needs to be coarse-grained to get badleites out of it, didn't have paleomagnetic data on it, but the dikes that had paleomagnetic data on them couldn't get badleites out of those. So it should be taken with a little bit of caution, but it is interesting that our pole looks very similar to this Harihaldi dike pole. It also looks very similar to the well-dated Chhattisgarh succession. So these similar succession that's recorded in the Chhattisgarh Basin and Pranita Godavari Valley Basin, which is also supported by a positive intraformational conglomerate test. And it looks similar to the Bhima and Kalatji Basin. And together, these poles actually define a paleolatitude, the Carnoul group. If this is primary, which it looks like it is, it actually defines a paleolatitude of 72 degrees away from the equator. So pretty much in polar waters. So what I wanted to do next is all the comparisons that we know, or all the compilations that we know for carbonates, has essentially been done for the Phanerozoic. We don't have a compilation for much of the Precambrian, actually. And so to evaluate the temporal and spatial context for the Purana platform, so we compiled actually paleolatitudes for the Proterozoic. So from 2,500 up to 540 million years about, we looked at platform carbonates that had paleomagnetic data that were listed in the global paleomagnetic database, as well as also, so not just direct constraints on platform carbonates, also indirect constraints, because often the paleomag was done on different rocks, not on the carbonates themselves, but within the dates, those it actually constrains the platform carbonate development. So we looked at all of our data that is in the global paleomagnetic database, but also those that were published more recently. And so that's nearly 2,600 records, paleomagnetic polls or studies. And so what we did, first of all, as a first looking at this data, is we actually kicked out all possible overprints. So basically, there had to be a presumption that the age of magnetization is the same as the age of the rocks that were sampled. So, and so we did this fairly indiscriminately, taking out all possible suspected overprints. Then we also didn't include data that came from data catalogs. So people who are familiar with the global paleomagnetic database would know that there's quite a lot of data from that is sitting in data catalogs, particularly from the previous, former Russian Soviet states. And we also didn't include unpublished thesis data entries that are, there's not many of them, but where they are, we actually didn't include them in our compilation. So often studies in the global paleomagnetic database also represent people who have gone back to a unit. So a lot of the studies have been superseded by more recent studies. And so basically we also excluded the superseded older studies. Some duplicates we kept where the two studies were completed independently and sort of around about at the same time. So there we included both for a specific unit. And we applied extra caution for studies that are older than 1980 in the global paleomagnetic database, because modern stepwise demagnetization and least squares analysis of data was only introduced in 1980. So the ones before 1980 need a little bit more caution. Also, the ages in the database is not updated, so we had to review the age assignments for the rocks. And then we actually also evaluated the quality of the paleomagnetic data using the R scale. We actually didn't use the quality or the R scale as a filter to filter the data, so we show everything that ends up in our compilation, but we indicate the R value when we actually look at the data, so that we are aware of what is the quality of the data that we're actually looking at. And so if we look at going through all of that, we ended up with about 140 platform carbonate units for which we have paleomagnetic constraints between 2,500 million years and 500 about. And so this is where the data is coming from. So you can see most of the data is actually coming from Laurentia, Siberia, North China, Australia, and South China. And so just some of the units here that you can see for Laurentia, of course, include the Belt supergroup, the Mackenzie Mountain supergroup. For Siberia, it includes most of the Siberian platform data from the Riffian. From North China, the Hawabai group, from North Australia, MacArthur Basin, Amadeus Basin. So each of these are actually identified in our compilation, which platform it's part of, also its thickness, so that we can look actually as a proxy for the volume of a deposit of a carbonate platform that was actually deposited. And so when we look at all of this 140 data points and we look at them in terms of the paleolatitude through time, this is the picture that we actually come up with. So each of these points is a paleomagnetic study of a carbonate unit. Okay, of course I show the age uncertainty, and for some of them, particularly some of the ones from Siberia, you can see the age uncertainty is massive, but we still include it within this compilation. So we didn't, as long as there was a presumption that the magnetization is the same age as the age of a rock, we actually included it. So we didn't filter it for the first quality criteria of a precise age. So we didn't worry too much about that. But so the color of these little dots actually shows its quality. So the lighter ones are ticking the box for fewer of the 7 R or quality criteria that we use in paleomagnetism. And the darker ones actually score a lot more of the points for data quality. So the darker the point, the more reliable it is, one could say, or could argue. And the ones that have actually a little red ring around them, for them, actually one of the data quality criteria that they satisfy is that the remnants is, the age of remnants is actually supported by a field test. So these are really the ones that we feel are very, very reliable, are the ones with the red circles around them. So the first thing that you can see when you look at this compilation is actually that most of the data, as expected, actually conforms to Phanerozoic extent of platform carbonates. So 95% of the data is actually sitting pretty much in the tropics and subtropics. Okay, some of them are a little bit higher here, but you can see that's markedly fewer studies here between 40 and 50 degrees compared to what is sitting between the equator and 30 degrees. All right, so most of the data actually conforms to our presumption that carbonates in the Precambrian were shallow shelf carbonates were deposited in the tropics and subtropics. Okay, there's a few studies only, and only 5% of the studies about are actually giving us higher paleolatitude constraints. And so the fact that we don't see them anywhere else, of course, doesn't mean that high latitude carbonates were not deposited in the Precambrian, because like all rocks, carbonates are also affected, their preservation is affected by an age bias. So as you go back in time, the likelihood that you preserve them gets less and less. And actually you can see that our data compilation, actually there's a paucity of data really here older than about 1.7. We have very few studies actually to fill the space here. Also, carbonate preservation, carbon deposition, and its ultimate preservation is also heavily affected by the supercontinent cycle, because the supercontinent cycle affects sea level and flooding of shallow shelf areas. So we don't form carbonates equally throughout Earth history. And so that can also have an effect on distributions that we look at here. Also, to have high latitude shallow shelf carbonates, you need to have continents at high latitude. And also, it's not a given that you're going to have continents at higher latitude throughout Earth history. And then the space that you have at the poles for continents is actually a lot less than what you have at lower latitude. So you can actually pack most of the continents at low latitude and have the poles free, but you can't pack all the continents at high latitude. So all of these are limiting effects or maybe biases in the preservation of potentially for high latitude carbonates. So if we look at these 5% of our data points, we can see that what are they actually representing? Well, these 3 points here is actually representing the Purana platform in southern India, and it's supported, like I showed you, by reversals as well as positive field tests, both fold tests and intraformational conglomerate tests. But then we also see this data here, these data points here, which are actually coming from North China, from the Nanfen Formation, the Xingxing Formation, and the Liu Lao Bai formations. North China, and they are kind of overlapping in age. Yeah, so they kind of at the same time as these studies from southern India, and they also very high latitude. And so the first thing one has to think of, because they occur at the same time, is maybe they are a mutual record of this high latitude carbonate platform. And if we can actually make a reconstruction here, just before during the assembly of Rodinia, where actually southern India and North China can be sitting here at very, very high latitude in close proximity. And so this possible close proximity between North China and India have been noted before, even in some models of Nuna or Columbia. So you can see it here. There's India and North China. Here's India and North China. So this might have been a longer-lived connection that actually survived initial Nuna breakup into assembly into Rodinia. Okay, so the second group, so we have this older group of high latitude directions, and then we have this younger group here at about 800. That's represented here by two studies, the Yinguru Formation of North China and the Madiyi Formation of South China. And unfortunately, none of these two studies is actually supported by field tests, so they don't have little red circles around them. But there is reversals recorded in the Madiyi Formation from South China, but also the paleolatitudes, the calculated paleolatitudes actually overlap with the Phanerozoic extent of carbonate platforms. So maybe these are less of a strong argument for high latitude carbonate deposition. So how do we explain these voluminous carbonate platforms at high latitude? Well, first of all, one can look at non-actualistic explanations, like the proposal that the Earth had a high obliquity before the Cambrian, in the Precambrian, because it has been explained by Williams, for example, that this would actually explain low latitude glaciations, and that we have this changeover or the switch in distribution of glacial rocks from the Phanerozoic to the Precambrian. Of course, we don't really see a switch in the occurrence of carbonates in the Precambrian year. We actually just see sort of this one time at the end of a Mesoproterozoic where we see high latitude carbonates forming in North China and southern India. Another way to possibly explain them is that the Earth's magnetic field was not dipolar at the time. So a typical dipole field, you'll get your highest inclination data at the poles, okay? The highest magnetic inclination recorded at the poles. But we might have had a quadrupole or an octopole component to the geomagnetic field. So a strong quadrupole component would actually you'd be able to record very high inclinations even at the equator or at mid-latitudes with a strong quadrupole component. But these components would really have to be quite dramatic, their contribution to the geomagnetic field. And of course, the work from Dave Evans in 2006, looking at evaporite deposits through time, has actually shown that for most of Earth history, these evaporites actually occur where we expect them to occur. They occur in the around close to the equator, between about 10 and 30 degrees, in sort of these dry belts around the Earth. And it suggests actually that the Earth's magnetic field was, for most of its history, dipolar. Okay, of course there are some gaps in here, but I think it is quite unlikely that we had such a strong octopole or quadrupole component to explain these high latitude carbonates in India and North China. So the only other way that I could think to explain them is actually that we're dealing here with a climate paradox, and actually they're actually a proxy for paleoclimate, okay? And probably are pointing towards a much hotter Earth between 1,200 and 1,000 million years ago. If our modern analogs for carbonate deposition is correct, this would imply polar seawater temperatures of above 20 degrees Celsius. And so, of course, we know that the Mesoproterozoic was a much warmer time, for example, than today, because the Earth doesn't record any glaciations here in the boring billion between 1.8 and 0.8 billion years. So to explain an Earth with no glaciations, of course, what we see is we need probably quite a lot more atmospheric CO2 to counteract the faint young sun at the time. And so to get a minimum required atmospheric CO2 to have no glaciation, we can model that, and here it has been modeled for polar temperatures just above freezing, so just above minus 1.5. And we see that we probably need about 10 times more present atmospheric levels of CO2. And if we actually look at what the rock record tells us, it actually shows us that most paleosols actually suggest that CO2 was a lot lower than what would have been required to produce no glaciation. But there's also some other data that actually, like from paired carbon isotopes, that suggest CO2 might have been enough actually to produce that type of warming to have no glaciers at the poles. Okay, but so this is for a polar temperature of minus 1.5. If we had polar temperatures of 20 degrees, it would suggest that we actually need a lot more CO2, which is not shown here in the rock record. And so to get around this problem of not enough CO2 or very low CO2 in the atmosphere, Sheldon and others have actually modeled that if you add methane to the atmosphere in different ratios, you can actually get ice-free poles. Okay, so here you can see the annual mean sea level, sea ice. So basically at the poles have no ice, but for that at 10 times present atmospheric levels of CO2, you would need about one methane molecule for every 20 CO2 molecules. So if we want to do this not at just ice-free, in other words, polar temperatures of around freezing, but actually polar temperatures of 20 degrees Celsius, it would imply that we need much more other greenhouse gases other than CO2 in the atmosphere at this time. So in other words, we need a super greenhouse climate at the end of the Mesoproterozoic. And so perhaps we can compare that to the end late Cretaceous and the Eocene, which is one of the warmest times in the Phanerozoic. And here we actually see a temperature gradient between equatorial temperatures of about 35 degrees, going to the poles at about somewhere between about 13 degrees and maybe 21 degrees. But if we look in the Cretaceous, shallow carbonate platforms only extend up to about 40 degrees from the equator. So this would suggest actually that if there was a super greenhouse at the end of the Mesoproterozoic, it was probably much more extreme than even the Cretaceous and the Eocene. So in some conclusions, the Purana Basin sequence free reliably record a primary magnetic signature of these voluminous carbonate deposition, and it suggests that that occurred at very high latitude, at about 70 degrees. This seems to be possibly unique to the end of the Mesoproterozoic, because this is the only time when we see these high latitude carbonates being preserved. We see them in both South India as well as North China, suggesting maybe that these two cratons also have a shared history and were probably in close proximity at the time. But it would actually require much higher amounts of greenhouse gases other than CO2 to sustain these warm polar temperatures of more than 20 degrees. So we would need a super greenhouse. But that is with a caveat that actualistic models actually apply for deposition of carbonate platforms in the Precambrian. So that is it from my side. That is my talk, and I'm happy to take your questions now.
All right, thank you, Michael. Can you hear me?
Yeah.
Okay, great. So we're going to switch over to question session. So you can find a way to raise your hand at the bottom, go to reactions at the bottom of your screen, and that very bottom button there is raise hand. You can also just type your question into the chat if you'd like, and I can read it aloud. So yeah, Michael, we don't usually stop the questions until they're done. So if you need to go sooner, let me know.
Sure. No problem.
All right. We have a hand, it looks like. Let's see.
Yeah, Paul.
All right, Paul, go ahead. Yeah.
Yeah, this is a fascinating and I think a very important problem, and I congratulate you for a pretty thorough job. I think it's a bigger problem maybe than you think, because I don't think you can explain high latitude carbonate production by having a warmer global climate. Okay, so preference for carbonate production is relative temperature, not absolute.
Yeah.
So saturation state in the cooler areas is limited by carbonate production in the warmer areas. Okay, so that's the first point. So I really think it is a big climatic conundrum, and I tend to believe in that basic carbonate chemistry applies throughout geologic time.
Yeah.
The second point I want to make is that I think that reverse weathering is probably the easiest way of getting a warmer global climate. Because you're simply kicking a part of the CO2 you consume in silicate weathering, you're kicking it back out again. So you have to have a warmer climate and a higher CO2 to keep the carbon cycle in balance. And I think, as Eason and Planowski have suggested, a higher silica concentration in the absence of silica biomineralization might be a key to significant rates of reverse weathering, which is basically clay mineral production on the seafloor. My last point is a terminological point. Let's not use the term super greenhouse. The reason super greenhouse has a very specific meaning in atmospheric and climate science. It's when the lower troposphere becomes water saturated and therefore opaque to outgoing long wavelength radiation. And it's considered to be transient and local. And when it becomes universal, that's the Venus-like,
So that's not what I mean.
So that's a very specific meaning in that science. So to help interdisciplinary communications, let's use ultra greenhouse, but not super greenhouse.
Okay, no, point taken. Thank you very much for that, Paul. Really appreciate that.
And I think it's a fascinating and important study.
Thanks.
Okay, Lee Kump, you're up next. Please go ahead.
Yeah, just want to amplify Paul's praise for your work, and really, really nicely done, and an important problem. I think to pick up again on the constraints, you're focusing on the climate constraints, but an alternative interpretation of modern carbonate distribution and paleo is around saturation state, not necessarily just temperature. And so the extent to which sufficiently high saturation states existed at higher latitudes in the past might be more tied to the carbonate chemistry of seawater, which is of course related to CO2, but also in the alkalinity content of the ocean. And then that brings in questions of weathering versus reverse weathering that Paul said. So a broader constraint might give some alternatives to that really high warm greenhouse effect The phase of carbonate precipitation, ichthyoid stability at low temperatures, for example, maybe is another consideration. But maybe just in your thinking, think about alternatives that are saturation state dependent rather than just temperature.
Sure. No, thank you. Point very well taken. Yeah.
Paul, go ahead to chime in.
Yeah, just to amplify Lee's point, very warm climates do tend to be more equable. And so that, leads to a situation where regional sources of alkalinity, like Emily Gaiman's idea about the Bahamian mud being related to Mediterranean outflow, might come into play. But 70 degrees is
it's extreme. Yeah. Yeah, we were initially very, very worried that we're looking at a magnetic overprint.
I meant 70 degrees paleolatitude.
Yeah, paleolatitude. Yeah. We were very concerned about overprints, because carbonates are not exactly the easiest rocks always to work with magnetically. But the 140 that ended up in our compilation, there was so many carbonates that we had to ignore because they were shown to be have magnetic overprints in them. But so these ones, I think, are really primary signatures that we're looking at, and I really have to think.
Well, cap carbonates are the rare example of carbonate that extends to fairly high latitude, but that's because there's an unusual state of carbonate oversaturation in the ocean.
Yeah.
Partly because you warm the entire ocean by 50 degrees. Or more.
Okay, and next we have a hand from Shihong Zhang. Please go ahead.
Okay, thank you. Great talk. Thank you. I would like to make a comment on the database, the paleomagnetic database. Can you show the slide 55?
Yeah, sure. Let me just go back to that. Whoops. Now I want to go back. So I want to go back to
the 55.
55.
Yeah, 51. So
55,
okay.
I can also show. Yeah.
All right. Okay, 55. Yeah. The comment is about the records of 50 and 74. Just now you mentioned that 74, 50, one is Ma-Di, another is Jing-Er-Yu formation.
Yeah.
For the Jing-Er-Yu formation, I think you use the old data for the Jing-Er-Yu formation. The paleomagnetic data is old one. Yes, I would like to tell you some additional information is that we redo that. We redid that to get some very high paleolatitude. It's very similar to the
also very high paleolatitude.
Yeah. Yes, very high latitude. But the problem is the age. The Jing-Er-Yu formation has no age at all. So we would like to credit it to the Nanfen formation. That means they are same.
I see. So it might actually extend.
You can remove the data. You can remove this support from the map. For Jing-Er-Yu.
Thank you very much for that. I mean, that's another problem with these things is actually the age data. I mean, because these ones from India as well, they're not particularly well dated. And we've really tried with glauconite and all of these things, but they're very difficult units to actually date. Yeah.
Okay. Another is Ma-Di, but Ma-Di formation has not carbonate at all. I think Paul knows this well. Before in the current time, South China has no carbonate in the Tonia and the Caledonian. Time. So you may delete the Ma-Di formation from this map. So so now the records only left is India and the North China Nanfen formation and their equivalent to the Nanfen formation. The age of the Nanfen formation, the age constraint I think it's better than that in India. I noticed that the rock and the rock magnetism are very similar between the two continents, between the two formations. And the Nanfen formation is constrained. The map is very good. So if the two studies are same thing, it's like in the reconstruction, if India connected to the North China, they are together. And were located in the high latitude. So high latitude, that's the polar zone, the polar region. So this is only one event in so far we find in the geological records. If they are
seems to be unique.
If they are not one event, that's a two. That's very interesting. About that. So another records I think you can discuss is between the carbonate rocks, the carbonate records and the clastic records. In Laurentia, it is the same time that is the clastic records. Also in the very high latitude, they may be formed in different the sediment environment. I don't know the reason, but the different phases, sedimentary phases. In Laurentia, that is clastic in the middle continent rift basin. That is clastic. The same age is clastic. Okay, this is the only I have only these comments.
No, very good comments. Thank you very much for that.
Okay, I'm gonna swing back to the chat for one from Karthik Sender Sarwan. Has the teratology of the Bruchevella microfossil present in the oak basin been studied? Do they show any anomalies or patterns which might help us in this climatic conundrum?
No. So they've just reported the micropaleontology. So there hasn't been any other more detailed study of those microfossils.
All right.
Not that I'm aware of.
Okay. Paul, did you want to chime in again or no?
Well, just about the fossils, the spiral form you showed looks a lot like Greipania, which in Laurentia is in rocks at around 1.9.
Yeah, which is a lot older. I mean, that's the feeling that I got also when I was reading about those microfossils, that they're not very, the particular fossils that they found in the oak were not very diagnostic in terms of the timing. That the new Proterozoic age is what the paper reported, and I mean, I'm not really well versed in microfossils, but I mean, so I just went for that. But it seemed, the feeling I got was that they're not very diagnostic.
No. And I just wanted to echo what Xiong Zhang said. I'm a little worried about the Nanfun formation ages in Liaoning Peninsula. A lot of them are zircon dates from mafic sills, but they're rather similar to detrital zircons in the same succession. So my concern is that the zircons in the mafic sills are actually xenocris. Look,
I mean, that's the real problem, I think, is actually the age data. But you know, beside the age data, you know, these carbonates are high latitude, you know, no matter whether they are a billion or 1.2 or 0.8, I mean, they are high latitude. We still have to explain them, but the ages are a problem. I mean, it's really difficult to get around that. That's why I actually included all of the data, no matter what the age constraint is, as long as that presumption of primary magnetization is there.
I think you make a very strong case for primary remnants. So then the question becomes GAD. But you really need extreme non-dipole components to actually produce these steep inclinations at lower latitudes, you know. So I think it is
very difficult. I think it's very unlikely. You know,
All
you
right,
can maybe
Daryl.
get away
Oh,
with
sorry.
15% contribution or you know, 20% contribution, but you need a lot more than that to produce these steep inclinations. I think.
Go ahead, Daryl.
Okay. Did you find any peculiar carbonate textures, anything distinctive that was different from normal systems?
No, they're essentially very macritic, you know, very fine-grained. Nothing strange about the textures. Yeah, pretty massive and pretty boring actually to look at under the fin section.
Did you get any molar tooth in those?
No, I didn't.
Okay.
Well, could they be, you know, could they be contourite drifts?
I mean, some of the pink carbonates higher up and the gray carbonates maybe. The lower pink carbonates not so much because they interbedded with the siliciclastics as well, and they start to become sort of wave laminated in the lower part of a succession where you go over from the Banganapali into the carbonates. So I think there is this shallow to deep facies pattern there. So for some of them maybe contourites, but yeah, not all of them, I think.
All right.
I mean, contour currents can occur at many depths on a,
Yeah,
you know,
and they can be wave laminated, of course. Yeah.
Another one in the chat. From Karthik, would a magnetic reversal generate such steep magnetic behavior?
Yeah, I mean the magnetic reversals, you will get them at globally at all inclination levels, right? So at the equator, you will just go from flat northerly to flat southerly, you know, and it's actually more prominent. The inclination difference is actually just more prominent at the poles, but you actually get this whole 180-degree swing no matter where you are on Earth, you know, so during a magnetic reversal. So I'm not really sure exactly what is meant by would the reversal produce these steep directions.
is the secular variation consistent with high latitude?
That's something that I still have to look at and test. I haven't actually done that. That's a very good point. I should really do that.
Be good to do. Big declination, small inclination change.
Yeah, absolutely. Yeah, no, that's something I definitely have to do.
All right. Well, it looks like we're out of things. So anything last minute someone wants to talk about?
Yeah, great study.
Cool. All right. Thanks a bunch, Michael. It really is cool to see this stuff.
Yeah, thank you very much also for everybody for their comments. It has really helped me, I think, quite a lot to rethink some of the things and putting me on the right track for where I have to go next to try and explore this a little bit further. So I really, really appreciate that.
Great. All right. Well, thanks everybody. See you next week. Take care till then.
Thank you. Bye-bye.